or checks or anything like that. You can get maximal efficiency out of these things. And then you also get sophisticated interprocessor communication. Why? Because you can pass data amongst those thread processors if you need to through shared memory. And that shared memory, again, is in a parallel cache, and it's very, very efficient. And then, so that cache parallelization, it addresses a fundamental shared memory problem that every supercomputer runs into. Every significant supercomputer design, very careful attention has been paid to memory architecture, and this, by the way, is one of the downfalls of FPGA, because not as much thinking has gone into memory architecture. And then also the fact that you can obtain very high radix concurrent memory access greatly facilitates the overall speed of the algorithms that you're running. And then you also have a natural floating point processing. Every thread processor has, in this case, a single precision floating point engine. And I'll tell you right away, double precision is at the moment a bit problematic for the GPUs because the peak throughput, for the NVIDIA devices, there's about a 90% penalty for, hi Neil, good to see you. There's about a 90% penalty for double precision. And I think for the ATI devices, they have a bit better implementation. It's about 50%. And then also something that's going to be relevant to the latter part of this discussion or this presentation is the fact that you have some very nice existing IP libraries that you can tap as building blocks. So let's talk a bit about those building blocks. With regard to the ultra large-scale FFT, I'm talking about the NVIDIA CU-FFT library. This is a very, very nice library. It's very highly optimized, not only algorithmically, not only in terms of the expression of the butterfly network, but also in terms of their use of this of the cache architecture, in particular the texture cache, which exploits the spatiotemporal coherence of the data. And it's essentially arbitrary, even odd radix. You can mix and match these guys for mixed radix as well. Although when you go to odd radix, the implementation, the penalty, you get about an order of magnitude reduction in performance when you go to odd radix. So again, even radix is preferred. Now here's something interesting. The CU-FFT library, in and of itself, as it exists today, can support full complex FFTs up to 8 million points. This is incredible. And I'm going to show you some benchmark data toward the end of this presentation. It's pretty amazing. And then also when you combine this capability with the fact that you have a streaming processing model, which is essentially SIMD or SIMT combined with asynchronous reads and writes to these devices. What we do is we exploit all this structure within context of mapping kernels to a GPU array, not just a single GPU. And then also we can reuse the instruction pipeline, and that helps us to further amortize the I/O overhead that must be associated with any ancillary processing device that might be connected to a CPU. So let's talk a bit then about CU-FFT-based ultra-large-scale FFT. So in present context, when I say ultra-large-scale FFT, what that means is a full complex FFT larger than 8 million samples. And also implicit to this is I can't really talk about the ultra-large-scale FFT unless I also talk about scaling properties as well. So in this context, I'm talking about linear scaling as you make these FFTs bigger and bigger. So here's a question, and I've posed this in a manner that allows me to introduce our technology very nicely. Can these CU-FFT designs be leveraged as ultra-large FFT building blocks? And of course the answer is yes. And in general terms, the way that we do this is the following. We take the original butterfly network for an FFT that might be billions of points, we reorganize that network into ultra large scale or ultra large fly instances. Radix 1024 is no problem, and higher is no problem. So then what we do is we take those FFT instances and we append a phase factor and address shuffle operators to those in order to reconstruct the original butterfly network. And so what that means, again, is that those CU-FFT instances, those FFTs, then become our ultra-large radix flies. And so the missing piece here is an appropriate processing model. Now, what I'm really claiming here is that using GPUs as a vector coprocessor isn't really good enough. And why do I say that? Because our goal is to accelerate complete scientific applications. And complete scientific applications typically consist of more than one, actually they may consist of many distinct algorithmic kernels. And so what that implies is that we want a processing model that exhibits a number of degrees of freedom that allows us to exploit all processing resources, not just the GPUs, but also multi-core CPU and cluster resources as well. So in order to exhibit those degrees of freedom, what that really means is that we must have a scheduler function that does a map and reduce that allows us to optimize the matching of algorithmic kernels to the processing resources in question. So what we've done with our EPX software framework is we implement a true supercomputing model within the application. And the reason that we do this is two of our design constraints, or two of our technical constraints here. There's a little bug flying around me, sorry. Is that we want to use standard operating systems. And right now, we can develop applications for Windows, both Windows XP, Vista. Vista is somewhat questionable because some of the drivers for our various APIs aren't quite stable yet, so we've tended to focus on Windows XP. What was I going to say? Yes, and also Unix and the various flavors of Linux, and also Mac OS X. So what we want to do here is to address coprocessor performance issues that we've identified in terms of maximizing the cyclostatic residency of a given instruction pipeline. We want to keep it there as long as possible. And so what that implies is that when we do the scheduling, when we do the mapping and scheduling, that we want to take advantage of opportunities to reuse the instruction pipelines and also to amortize I/O costs as much as possible. And then what this allows us to do is to maximize the effective parallelism over the set of diverse algorithmic kernels and also the processing resources involved. So our generic architectural components in our EPX framework is a scheduler, a dispatcher, and a scatter-gather engine. And we add that to the application. It's part of our software architecture, and virtually everything that we build has pretty much the same architecture all the way down to the dispatcher, which actually creates the threads that are mapped to the GPUs or to multi-core or what have you. And this is actually very convenient for applications development, as you might imagine. So ultimately, what we're looking for and what we do achieve is a linearly scaled performance and that relationship is actually a product here, the number of GPUs times the number of thread processors per GPU times the number of CPU cores we have available times the number of nodes. And we're seeing this type of scaling performance for a number of applications that include Monte Carlo, computational fluid dynamics, finite element, boundary element, and also FFT type calculations.